All right, so now we move on to 3.2, which is two variable equations. Problems containing two unknowns are called two variable equations. One such family of equations is called the Diophantine equations, named after a famous Greek mathematician. And it's named after the 3rd century mathematician who lived in Alexandria. It is through his major work, Arithmetica, that his influence has reached modern times. Collection of work divided into 13 books, which have of which 6 have survived in Greek and 4 in Arabic version. And so, collection of 130 problems in algebra. The major advance was in the introduction of symbolism for the solution of equations. Egyptians, Babylonians wrote out equations and solutions in words. Diophantus explored the idea of using symbolic notation, and so therefore became considered by some as the father of algebra. Right? So the Diophantine equations, in this category of two unknowns in one equation, in general, such problems have had fewer equations than variables. Right? Yeah. Okay. Well, we'll discuss that a little bit more later. Diophantine equations have integer coefficients, and we allow variables to take positive integer values only. All right, so there are some restrictions to these types of equations that apply in this situation that don't always apply. All right, a linear Diophantine equation in two variables is an equation in general form. Now, this is called by many to be the standard form of a linear equation. So I'll make a little note, also known as standard form of a linear equation. And this is, if you're ever to take a linear algebra course, this would be day one. All right. So such an equation has integer solutions if and only if D divides C, where D is the GCF of A and B. All right, it's the greatest common factor of A and B. All right, and when we say if D divides C, that's just kind of like a weird, archaic way of saying it. But a wordier version, which is what I'm about to say, is you may not find that to be better. All right, so this is saying that C is divisible by the GCF of A and B. All right. So let me, before getting into the printed example one there, I'll just do a quick side example. Let's say you have 3x plus 4x is equal to 24. All right. So the greatest common factor of 3 and 4, I don't know why I put an X there. 3x plus 4x plus 4y. Should have been 4y. So I'd find, so this is my A value. This is my B value. We're looking for the GCF of A and B, which is really the GCF of 3 and 4. The greatest common factor of 3 and 4 would be just a 1. All right. So if you look at the example that they have here, the greatest common factor of 6 and 51 is 3, and that's because 3 is the largest number that divides evenly into 6 and 51. All right. So then what this is saying is if 24 is divisible by 1, which it is, there must be an integer solution, all right? All right. And that's what's happening here. So there is a set of integer solutions. And when I say an so I'm kind of using that term loosely, I guess, but an integer solution, since there are two variables, that means that it applies for both x and y, which means that there is a pair of values, one for x and one for y, that would, using integer values only, satisfactorily solve or provide a solution to this equation. So what I would do is make a table of values. Now the technique that you'll see in this text is it's a lot, because the table of values involves solving the equation for y in terms of x, which makes, in some cases, a pretty nasty fraction. What we could do instead is we take our equation, 3x plus y plus 4y. We're still going to use the idea of a feasibility table, but I'm only going to focus on 3x and 4y, kind of like before when we did the check for in the last section when we were checking solutions. I would just focus on the left-hand side, because if the left-hand side of the equation simplified down to give me whatever is on the right-hand side of the equation, like it happened here and here, then I would be satisfied that that was a valid solution. So that's what I'm going to do here, is I'm going to take values of x and y and start plugging them in, right? The only difference here is it's just a kind of a question of where you start, all right? So we construct, we're only looking for to yield positive results. We construct a table with two good solutions, and then increment or decrement from there to find the remaining ones. All right, so I'll show you in their example how they played that out. So they solved, and then, like I was saying before, you plug in some values, and it's not pretty, all right? But I mean, it's doable. It's just there's just a lot going on here, all right? So we would probably want to streamline that somewhat, all right? So we'll do that here, except I'm going to make a table of x and y, and then we'll apply the relation, or the expression that's on the left-hand side of 3 times x plus 4 times y. So we could start, it says to start that we should expect only positive integers, so 0, 0 wouldn't necessarily work. But you could try it anyway, because you never know. But if I do skipping over 0, 0, and even you could just do the mental math on that, you realize it's not going to work. But you might try a 1 and a 1. 3 times 1 plus 4 times 1 is not going to work. All right, that doesn't get you a 24. All right, so I can increment up either my x or my y. It doesn't make a difference. All right, I tend to keep one constant while moving the other. But if you think about it, we need to get to a 24. So if I did 2 and 2, that would give me a 6 and an 8. That's not quite there. So 3 and 3, 4 and 4. You know, you might kind of jump around based off of what it sort of makes sense to do. All right, so I could try 2 and 2. That'll give me a 6 and I think I just said that. 3 and 3. So that'll give me a 9 plus a 12, which is 21. So if I tried 3 and 3, that's not good either. So out. But now I might say 3 and a 4. All right. 9 plus 16 is 25. We're trying to get to a 24, so not great, but maybe we flip it around. All right. 3 times 4 is 12. 4 times 3 is 12. This pairing checks out. So we have a solution of 4, 3. All right. I'll show you a graphical approach down the line, but for now we'll just focus on the numbers. All right. So if I were to say All right, so I'm comfortable with this. I might try to increase the x value again. In order to do that, I would decrease the y value, just to kind of keep it balanced. So let's say I'm going to 5 here. That's a 15 for my x's. I need to get to 24. Am I going to do that with only whole number multiplier of 4? Right? So no, because I need to add, to get from a 15 to a 24, I need to add 9, and there's no value, no whole number value I can multiply by 4 that's going to do that. So I would wipe out my 5 as an option. I'd try 6, 18, right? I would need to go 6 more, still not going to happen, right? So I think we skipped over 2, so I would try 2. That gets me a 6. In order to get to a 24, I would need 18, so that's not going to do it. All right. You could, if you want, you could play around with multiples of 4 to get started. All right, and just see where that gets you. But it really is just a matter of continuing the process to see if you come up with a valid second solution. And bearing in mind, there may just only be the one solution. Right, so that's something to consider, and there is value in that. Now, one other thing, so this tells us that there is a guaranteed solution in here. An equation has an integer solution or solutions if and only if D divides C. I'm looking for a second solution, but maybe there isn't a second solution to be had. Right, so if that's the case, we try all our different possibilities, and if we only had that one solution, that's perfectly fine, right? And in fact, when you're dealing with linear equations, that's often the way of it, right? Because you could have one solution, you could have many solutions, or you could have no solution. It is possible that you could just have the one solution, all right? So now, let me take you through their approach here. So we had 6, 51, and 22. The GCF of 6 and 51 is 3. Right? 3 does not divide 22. 22 is not a multiple of 3. That's the idea of it. We have the GCF. The 22 is not divisible by 3, so there's no solution. All right? So I just showed you an example of one solution. Here's one with none. And let's see what some other possibilities kind of lead to. All right. And again, the process is here. But you have a man sold his sheep for $60 each and cows for $80 each. He received a total of $840. How many of each animal did he sell? All right. So we're expecting whole number values. All right. So we're not going to get any negative numbers. We're not going to get half of a sheep. All right, so whether or not that's possible or based on how you consider things, but let's just assume whole number sheep, and cows. The translation, I think that's pretty straightforward, should be anyway. Checking to see if there's a solution. So the GCF of 60 and 80 is 20, and 840 is divisible by 20, so we're good there. We know that there's at least one solution. So what they do is they solve the equation for x, all right? So I'll just show the work on this. We had 60x plus 80y is equal to 840. We're subtracting off the y term, so 80y, which is not like the 840, so it's not a like term. So we leave them separate just as a difference, but we don't actually carry out finding the difference. And on the left, I can divide out the 60. If I do it on the left, I do it on the right. You can simplify this further, but for now, we'll just leave it like this. Each term is divisible by 20, so you could simplify it further if you want. All right. So the little notation here, isolating a variable with a smaller coefficient will result in a lesser possible values of the other variable in the next step. All right. So by solving, we had a choice between 60x and 80y. Why did we subtract off the 80y? The 60 is a smaller coefficient, which is it's gonna restrict the number of possible outcomes that you could have. All right. And the process behind this, if you solve, since we know that the value has to be greater than 0, we could, greater than or equal to 0, we could kind of clean it up and come up with we call it a feasibility interval, right? And that gives us values that we can test in the table, because the way I was doing it before, we would just kind of, I don't want to call it using common sense, but it's in the realm of number sense, where we had an idea, it had to be in this general neck of the woods. Like, for example, I could have, I suppose, tried testing out 300 as an X value here. And then I would realize, okay, that's not a good number to pick. If you don't really have an idea, then you're basically starting off with 1, 1, then going 1, 2, 1, 3, 1, 4, and so on. And if the solution is like 50 for X and 78 for Y, then you could be at it for a while. So this kind of narrows the field a little bit, right? But there's a lot of algebra in here that maybe you're not interested in doing. I don't know, especially since we're talking about sheep for $60 each and $80 each. If I think about it, you're just kind of using, again, not common sense, but number sense. I would be thinking, well, if I'm going to get $800, I'm not looking at anything more than like 10 or 11 cows if I were only selling cows, because 80 times 10 would be 800, 80 times 11 would be 880. So 10 to 11 cows at max. And then for the sheep, like 10 sheep would get you $600, right? So 11 would be 660, 720 would be 12, 13 would be 780. So we're talking about 13, 14 sheep at most. So I would be restricting my values if I were plugging and chugging away. I'd be restricting it to like the 5, 6, 7 neck of the woods, just to kind of play it out. This is a more formal approach to doing that, because what they did was they said, all right, if this number has to be greater than or equal to 0, all right, because maybe it's all cows, or maybe it's all sheep. We allow for 0 to be the other variable. All right, I'd cross multiply, because 0 I could think of as 0 over 1. So I could multiply both sides by 60, or cross multiply. $840 minus 80y greater than or equal to 0. Then I would subtract off the 840. I get negative 80y greater than or equal to negative 840. And then I would divide out the negative 80. You may remember this when you divide involving an inequality, you flip the direction of the sign. So y is going to be equal to, it ends up being 10.5. So whatever I select for y would have to be less than or equal to 10.5. So that's where a list of 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1 come from. All right, we wouldn't go down to 0, because we'd have to have, if there were 0, y is talking about, or I'm sorry, x is sheep. So if there are 0 sheep, I'd have to have at least some cows. All right, so that gives us a set of values, and then we could plug those values in and see which ones give us clean whole numbers. Now, in this case, you end up with 2 possibilities. So if I plug in a 10, I get a fraction. When I plug in a 9, I get a whole number. So that would be 2 sheep, 9 cows. Pretty sure it was sheep was the X. Yeah. All right. So it was 60 60, 80, right? So $60 on the sheep, so 2 times 60, plus $80 on the cows, so 120, plus 9 times 8 is 72, so 720, 840, which is, I believe, what the total amount was supposed to be. Yeah. So that's one possibility. The other is, and maybe you had 6 sheep, 6 cows. So that's 6 times 60 plus 6 times 80, which would give you 360 plus 480, which would also give you 840. All right. Now, we could also find any remaining positive solutions by determining the change in X and the change in Y that gets you from one to the other. All right. So, again, it's very procedural, and there's a lot going on here. But what this is saying is we have our two answers, 2 and 9, 6 and 6. Here, I'm increasing by 4 to get from a 2 to 6. In increasing by 4, I'm decreasing by 3. So an increment, a 4-unit increment and a 3-unit decrement. All right, so increasing by 4, decreasing by 3. I would increase and decrease by that same margin until I get numbers that don't make sense anymore. So I would get 10 here, so increase to 10, which is a reasonable number. I could sell 10 sheep. I'm down to 3 cows. All right, and I can verify that if I want to. Just kind of continuing like this. Maybe I'll just move this down so I can see it, like all in one shot here. So another possibility would be that I could sell 10 sheep and 3 cows. So 6 up. I keep wanting to take that first number. 10 times 60 plus 3 times 80. That's going to be 600 plus 240 is going to be 840. I could do it again, or at least try to do it again. We'll see. Another plus 4. Now I'm up to 14 sheep. Subtract off 3. I'm down to 0 cows. So 14 sheep, 0 cows. 14 times 60 plus 0 times 80. That's straight up 840. So that checks out also. If I were to try to do it again, I'll just show the act of doing it again. I'd get 18 and negative 3. But that would be out. That wouldn't make any sense, because what that would mean, and actually there is a school of thought where it makes perfect sense, but I'll just say for now it doesn't make any sense, because how can you have or sell 3 cows? What this would actually mean is that they'd be making change for you in terms of livestock. Like if something cost $2.50 and I give you $3, you would then return to me my change of 50 cents. Right? What's happening here, and you could make a case for this, would be I want to make $840, so I'm going to sell 18 cows. All right? But that would be more than the value that the person or that I would be looking to obtain. So to call it even, the person I was selling the 18 cows to, I would say, all right, well, give me back 18 sheep. I'd say, give me back 3 cows. That'd be my change. All right. So, and that would work out if I had maybe more sheep than cow, like a lot more sheep that I was looking to get rid of, which kind of sounds horrible, but treating it as a commodity, you can make a case for that. Right. So it just doesn't sound very ideal, but or ideal is not the right word. It just doesn't sound very, very nice to be trading in sheep and cows, but that is a way to make it make sense. Just like I was saying before, the idea of having like half of a cow, half of a sheep, it doesn't sound great, but there is a school of thought where that makes sense too. All right. But that's where all of this stuff kind of plays out. You get all these different possible solutions. And that's the idea. So example 3 just kind of follows the same progression. So you can look that overall. So same thing with 4. It's just a lot of extra practice with the same stuff. All right. So that brings you to 3, 2, 1, which is the Diophantine equations, part 1.